Hi students, and welcome to Preliminary Chemistry and the metal video series. We're going to get a double dose of history here because we had a little bit of a history of development of the atomic model, and in this video we're going to just quickly look at the history of changes in our understanding of the organization of elements in the periodic table. So whilst there are a lot of different ideas, really the first one who contributed to an actual attempt to organize the elements into some sort of grouping pattern was Johann Dobrynin. And this occurred in the early 1800s when he was observing some of the chemical similarities between what he called triads, or groups of three elements. And if you look at some of the groups that he looked at, chlorine, bromine, iodine, and lithium, sodium, and potassium, you might get a little bit of an understanding of why these particular elements actually did form some consistent patterns. And what he found was that the middle member of each of the triads he was looking at had atomic weight and different properties such as density that occurred as the average or somewhere in the middle of the other two. So he found some sort of a link between these little triads and obviously suggested that they must belong together. They must have certain things in common. But not only that, he also found some other interesting properties associated with his triads as well. For example, he found interesting patterns in reactivity. So we would know from lithium, sodium, and potassium that the activity, the chemical activity, increases as we go along this little triad. So lithium is less reactive than sodium, and sodium is less reactive than potassium. Of course, this occurs in the opposite direction for the chlorine, bromine, iodine group. But nevertheless, Dobrynin was one of the first ones recorded to have actually made an attempt to try and put the elements into some sort of a grouping pattern. The next to kind of expand a little bit on that was John Newlands, and none of this really happened for a little while because the way that elements were grouped together in the early stages was based on their atomic weights. And so we needed to have better ways of actually being able to measure that. And obviously in the 19th century, technology was limiting that somewhat. But in 1864, John Newland had a crack at tabulating classification based on atomic weights. And he later updated that table to have 8 columns and 7 rows, and we were already starting to get a sense that the number 8 was going to be very important in our study of elements. What Newlands found was that every 8 elements from a given starting point had some similarities in their properties and hence belonged in the same family. This started to create what he called the law of octaves, and the link with music is obvious for those of you who are musicians. The problem with this law was it wasn't consistent for all known elements, and obviously there were elements that hadn't been discovered at this time as well, so some gaps. And so some of those predictions were very good and very consistent, and others were not. This left the field open, I guess, a little bit for Dmitri Mendeleev. And in the latter part of the 19th century, he developed a periodic table that was based on both physical and chemical properties. And this made it a significant improvement on the previous work that had been done up to that point. He based his order on the order of atomic weights, and where he didn't know of certain elements, or if there were certain things that he felt belonged somewhere, if he found gaps, he just left those gaps and those spaces for elements to be discovered in future. In fact, one of the ones that he predicted quite closely was germanium. He called it ecosilicon and predicted that it would have properties very, very similar to silicon, in which it was just sort of sitting underneath that column, if you like, the groups as we now call them, in the next row or the next period. And he predicted the properties very, very consistently and very, very close to what they actually were when germanium was later discovered, much later. His 1871 periodic table had 8 columns and 12 rows, and he came up with what's called the periodic law, and we'll discuss periodicity in the next video. But effectively what he was saying was that the properties of different elements vary in a consistent or periodic way when measured against their atomic weight. So as we see the atomic weight increasing, we find patterns of periodicity. And as I say, we'll look at that in a little bit more detail in the next video. It's Mendeleev's periodic table that we use, with some minor modifications that have occurred since then because it was such a good job. A couple of people who contributed, Lothameyer, who was had a table that was very similar to Mendeleev's, and he was able to graphically demonstrate periodicity. So this was a more compelling, practical, observable phenomenon based on periodicity, although Mayer's was slightly inferior because he was focused more on physical properties of elements rather than the physical and chemical used by Mendeleev. William Ramsay added our last group, or our last column, to the periodic table as he and his team discovered a number of the inert gases, helium, neon, and argon, and these were later added to Mendeleev's table in the group that we now call the noble gases. Henry Moseley was working from a theory of Vandenbroek, who said that we should actually be arranging these on some different criteria rather than atomic weight, and he said that there should be a consistent number, and Moseley carried out some experiments with X-rays and found, in his words, there is in the atom a fundamental quantity which increases by regular steps as we pass from one element to the next. This charge within the nucleus we now know is a result of an increasing number of protons, and the increasing number of protons in the nucleus is now what we use in ordering our periodic tables. And so those numbers go up by atomic number, which is now the key, and that's how we arrange our elements. So just as with the atomic theory, we've just walked through some of the key players that have helped us to construct the periodic table in its current usage. Thanks for watching.